In this lesson, we're going to be looking at oscillations and normal modes. This is really useful because so many things are oscillations around some equilibrium position, be it vibrations in a material due to heat, or gravitational waves, or quantum fields, really. So once we get a hang of oscillations and normal modes, it really does apply to so many situations. Now, there are some prerequisites for this, so it would be really useful if you understood or are really comfortable with matrix algebra, specifically using Einstein's summation convention. And if you don't know what they are, then I would definitely look those up and get comfortable with it before this video. And secondly, it would be good if you've looked at simple harmonic motion and you've studied oscillations. Oscillations always occur around an equilibrium point or a critical point. And this is just a configuration of the system which, if we were to set it up in that configuration and just leave it, nothing would happen. And then if we were to move it a little bit, it would start rocking back and forth, oscillating around that position. So the first thing we're going to need to do is find where these equilibrium positions or critical points are. And mathematically, the condition for this is that qi dot and qi double dot are both 0. And this has to be true for all the different coordinates, so for all I. And what this really means is that the particle doesn't move and that it doesn't start to move. So we just put it there, leave it, and it will stay in the same configuration. This example here is probably the archetypal example for oscillations or simple harmonic motion. And this here is the Lagrangian for a mass on a spring with spring constant K. So in order to show that x equals x naught is a critical point, or an equilibrium point, we need to show that the equation of motion is satisfied by our equilibrium condition, which was x dot equals x double dot equals 0. And we want to show that that holds and x equals x0 holds all at once. So we'll see how that works. So we're going to start off with our Euler-Lagrange equation, do all those derivatives, and we get our equation of motion. Now we look at our equilibrium condition, so we set x double dot to 0. And then we're left with this equation. And this equation is indeed satisfied, that x equals x naught. So in other words, what we did is we got our equation of motion, set all velocities and accelerations to 0, and now we have an equation that just involves position. And then we need to solve for position. And that will give us our equilibrium configuration, or our critical point. This Lagrangian is one you've seen before, and it's the Lagrangian for a bead on a rod, and the bead can slide up and down the rod, but the rod is forced to spin at a fixed rate, omega. And we want to show that r equals 0 is a critical point. So I would recommend pausing the video and trying to have a go yourself using the ideas from the last example, then come back to the video and I'll go through the solution. Okay, now you've had a go, I'll go through the solution. So we start off with our Euler-Lagrange equation, then we get our equation of motion, we set r double dot to be 0, and then we're left with that last line, and the only way to solve that equation is to set r equals 0. Okay, this example is a bit subtle, so I'll go through the solution fully, but if you feel confident, have a go by yourself and then come back to the video. This Lagrangian is for a diatomic molecule, or something like that. It's a simple model of a diatomic molecule, where we just have two masses attached by a spring of length L. And in order to find the equilibrium position, we just do what we did in the last two examples, except we have to do it for both coordinates. So for our x coordinate, we take our x Euler-Lagrange equation, we do the derivatives, and we get our equation of motion. And then we use our equilibrium position, or our equilibrium condition, to set x double dot to 0. And then we are left with this equation to solve. Then we take our second, or y Euler-Lagrange equation, we do all the derivatives, we get this equation of motion, which is just like the x equation of motion, but with a sign difference before the k. And then once again, we set y double dot to 0, and we are left with this equation to solve. Now, in this case, both equations are the same, and that's, in this case, just a coincidence for this case. It won't always be the case, so you do still have to do it for both. And now we need to solve these equations to find x and y. So the first solution is x equals y plus L. And that will satisfy both of these equations, no matter what y is. So our y solution is, well, y could be anything. So let's just set it to y0, where y0 is an arbitrary value. But what does it mean that y could be anything? Well, that just means that the molecule could be anywhere. It doesn't matter where the molecule is. If you just take it and leave it somewhere, it will just stay still. What really matters is that the molecules, or the atoms in the molecule, are a distance L apart. So it doesn't matter where the molecule is, you can move it around as long as you don't stretch it or compress it. Later on, we'll see when we do stretch it a little bit, then it will start vibrating. But that doesn't matter. But what doesn't matter is where it actually is. Okay, our next Lagrangian you've also seen before. It's for a bead that can move on a wire loop, but the loop is made to spin at rate omega around its vertical axis. So have a go at this example on your own, and then come back to the video and I'll go through the solution. Okay, so now you've had a go, I'll go through the solution. We're going to start off with our Euler-Lagrange equation for theta, and this is our only coordinate. So we do all the derivatives and we get this equation of motion, which is quite long. And the first thing we can do is set theta double dot to 0. That's our equilibrium condition. And now we are left with this equation of motion, which we can factorize. This will make it a bit easier. And from here, you can see that there's multiple solutions. So our first solution is sine theta equals 0, which means theta either equals 0 or pi. And then our second solution is that cos theta equals minus g over L omega squared. And note that because cos theta has to be between minus 1 and 1, this solution is only valid for omega squared is greater than g over L. We are now going to rewrite our Lagrangian in a more useful way, and that is with a kinetic-like term minus a potential-like term. Now, almost all Lagrangians can be rewritten this way, and every Lagrangian we've seen or will see in this course can be written this way. And what is important about the kinetic-like term is that it's quadratic in the velocity. And notice I've said kinetic-like and potential-like. And that's because not everything that looks like a kinetic energy is going to be quadratic in the velocity. And if something in the kinetic energy isn't quadratic in velocity, then that term will be included into the potential-like term. So really, this first term isn't the kinetic energy, but the kinetic energy, with the inverted commas, or kinetic-like energy. And so notice that this first term has these I and j subscripts. That's because we're summing over all of the different coordinates. So we could rewrite this in matrix form. Okay, now let's look at some examples which might help make this rewriting of the Lagrangian make a bit more sense. So our first example is just two free particles with positions x and y. And there's no potential energy in this case. So in order to write it in matrix form, we can rewrite our velocities in one column vector. So we're going to call our q dot vector x dot xy. It doesn't matter which order, let's just put it in this order. And then our matrix K, which is going to define our kinetic energy, or our kinetic-like term, is going to be a matrix with little m and big M on the diagonals. And you can verify this just by doing the matrix multiplication in that first term. And you'll see that you get back to our Lagrangian. Our second example is a little bit more complicated. And so we're going to start off, again, rewriting our velocities in vector form. So we have r dot and theta dot. And in this case, both terms are still quadratic in the velocity, and so we'd still just have a kinetic-like term. And so our matrix K is going to be m and mr squared. And again, if we were to do the matrix multiplication, you would get back to our original Lagrangian. Now the final example is a bit trickier. We saw this example earlier. This is the Lagrangian for a bead on a rod that's forced to spin at rate omega. And if we were to interpret this, kind of using our Newtonian lens, we would see that this is just the kinetic energy. We have the radial and the tangential kinetic energy. But in this case, only the radial kinetic energy is quadratic in velocity. The r squared omega squared is just a function of the coordinate r. Remember, omega squared is a constant and it's held fixed, so that doesn't count as a velocity. Or at least it doesn't count as a generalized velocity, one that we can do our Euler-Lagrange equations with. And so we only actually have one coordinate in this case. And so our q vector is just r dot. There's no other coordinates. We don't need to really write it as a vector. Our matrix K, and again, it's just a 1-by-1 matrix, so we don't really have to make it a matrix, is just going to be m. And we can verify we get the first term, our half m r dot squared, by multiplying this out, as if it were a matrix like above. And then we also are going to have a potential-like term, where our potential-like term includes the terms that are not quadratic in our generalized velocities. And in this case, our potential-like term is going to be a half or minus a half m r squared omega squared, where the minus sign cancels with the minus v tilde in the Lagrangian, and we will get back to our original Lagrangian. And note, as we've seen here, that our matrix K will quite often be constants, but it could be a function of the coordinates as well. What's really important is that we're just including the terms that are quadratic in the velocity in our kinetic-like term. Everything that's not quadratic in velocity goes into the potential-like term. Once we have rewritten our Lagrangian this way, finding the location of critical points is much easier. So, the first thing we can introduce is generalized forces, and these are the derivative of the potential-like term with respect to one of the coordinates. And this is just like in Newtonian mechanics, where force is the derivative of the potential. It's exactly the same idea, except now they're generalized forces, because this is a potential-like, but also these are generalized positions, not just normal XYZ Cartesian coordinates. And our equilibrium condition is that these generalized forces are zero at critical points. This is just what we expect. When something's in equilibrium, all the forces acting on it are zero. The proof for this is in your booklet. So I'd say go through and annotate what's going on. It's a lot of algebra, but it just starts from applying the Euler-Lagrange equation to the rewritten Lagrangian from the previous slide. And there is quite a lot of matrix algebra going on. So this is where you have to be comfortable with Einstein's summation convention. We can now go back through our previous examples and rewrite them using the new rewriting of the Lagrangian and use the new criterion that the derivative of the potential-like term is zero to find the critical points. So for this example, for this Lagrangian, the matrix K that defined the kinetic-like term was just m. The potential-like term here is just our potential energy. And the critical point, we do the derivative of the potential-like term, which gets us k x minus x naught, and we set this to 0. And again, this is solved by setting x equals x naught. For the next example, I'd recommend having a go by yourself and then coming back to the video to work it out. I mean, you've already seen the answer and we've already seen how to turn this and rewrite it in the new way. So you should be able to do this one on your own. Okay, now you've had a go. I'll quickly go through the solution. So the matrix K for the kinetic-like term is just M. Remember that second term in the Lagrangian, even though it looks like it's part of the kinetic energy, or even though it is part of the kinetic energy, it's not quadratic in velocity, so it's not included in the kinetic-like term. And then the potential-like term is minus a half mr squared, omega squared. We look at the derivative of the potential-like term, which gets us this, and then we set that to 0. And this is solved by r equals 0, as before. Okay, we've seen how to split this up into K. We just saw a similar example of how to rewrite this in terms of a kinetic-like term. So have a go by yourself. Then if you can't get it, come back to the video and I'll go through it. Okay, so we can rewrite our kinetic-like term. So our matrix is just M and M on the diagonal, and our potential-like term is just the potential energy from the springs. Then our condition to find the critical point, we take the derivative of the potential, set that to 0, and we do the same thing for the y coordinates. We take the derivative with respect to y, get that, and we set it to 0. And these are the same equations we had before. So we say x equals y plus L, and y equals anything, so y naught. Okay, now on to our final example. I'll try and have a go yourself, and then come back to the video once you've had a go. But I understand this one might be a bit harder to know or to work out what goes into the kinetic-like term and what goes into the potential-like term. Okay, now if you've had a go, I'll go through the solutions. So firstly, the kinetic-like term will only include the term that includes theta dot, because it only includes terms that are quadratic in the velocities. And so in order to get the kinetic energy, our K matrix is just ml squared. Then our potential-like term will include both those terms that don't include theta dot. So our potential includes that first term, which is included in the kinetic energy, or was originally included or thought about as kinetic energy, and what was originally thought of as potential energy. So both of those get included in the potential-like term. And then we use our equilibrium condition. We take the derivative and we set it to 0. And we get the same equation as before, which is solved in the exact same way. So we have sine theta equals 0, or cos theta equals minus g over L omega squared. So what happens when we deviate slightly from the critical point? So if we're in equilibrium and then we move it slightly, we're not going to be in equilibrium anymore, and the force could either be back towards equilibrium, in which case the system will oscillate, or it could be away from equilibrium, in which case the system will just get more and more out of equilibrium. So in order to analyze this, we're going to expand everything around the critical point. So recall that our Lagrangian can be written as the kinetic-like term take away the potential-like term. And then what we're going to do is rewrite our coordinates around the critical point. So we take our coordinate qi and say that's equal to qci, where qci is the value it took at the critical point, and then plus eta. So eta is the deviation from equilibrium. In doing this, the kinetic-like term becomes this. Since qc is just a constant, that goes to 0 when we differentiate, and so we just replace the q's with the etas. The potential-like term is going to be a bit harder, so we start off with the potential energy, and then we can Taylor expand. So we start off with the value at equilibrium, we add the first term of the Taylor expansion, so the first derivative, And then we have the second derivative, and then 2 factors of eta, and then something that depends on order eta cubed. Now, that first derivative term must be 0. We're in equilibrium, and so that first derivative, by definition, is 0. And we're also going to ignore the first order, sorry, the 0th order term. Because if it's a potential energy, constants don't matter. You can shift the entire energy by a constant, and it won't affect the motion. So the potential energy term is just that second order quadratic term, that third term there. We can rewrite our Lagrangian as is on the screen. And notice now that both terms, both the kinetic-like and the potential-like term, are just quadratic. And it's the fact that they're both quadratic that's going to make everything nice and easy to solve. And now instead of Einstein's summation convention, we can rewrite this as a matrix, if that's clearer. Well, on the left, this K matrix is just a Kij as above, and this calligraphic V matrix is the matrix of second derivatives as above. And note now, because we have expanded around the critical point, everything has been evaluated at the critical point, and so K and V are now constants. Even though we didn't say it on the last slide, K has been evaluated as well at the critical point, but we didn't have to expand it since it's already a second order term. It's already associated with this quadratic factor of the velocities. For the next few examples, we're going to take all the examples we've been using so far and then rewrite the Lagrangian and expand around the critical points. And this is why in the previous examples, in the booklet, I gave space to explicitly write the kinetic-like matrix and the potential-like term. So for our first example, we rewrite the coordinates as x equals x naught plus eta. And we already know the kinetic-like matrix was just M. And then the potential-like matrix is going to be the second derivative of the potential-like function from before, and that's just equal to K. And so our Lagrangian, written in this form, just becomes a half m eta dot squared minus a half k eta squared. Because everything was quadratic to begin with, we've barely changed the Lagrangian in this case. Okay, for the next example, have a go on your own, and then come back to the video and we'll go through the solutions. Okay, now you've had a go. I'm going to start off by rewriting the coordinates as r equals 0 plus eta. Again, this might feel a bit trivial, but it's just so we can get used to the notation. So then the kinetic matrix is just M, like it was before. The potential like matrix, or the second derivatives of the potential, that matrix is given by the second derivative with respect to r, which gets us minus m omega squared, and then the Lagrangian is given by a half m eta dot squared plus a half m omega squared eta squared. And again, because this was already quadratic, the final result doesn't really look that dissimilar. It is just a coordinate change. Okay, we'll go through this next example. This one will be a matrix because we've got two different coordinates. So we rewrite off our x as y naught, as x equals y naught plus L plus eta 1, and y equals y naught plus eta 2. And our matrix K is just m's on the diagonals, exactly as it was before. And then our potential matrix includes all the second derivatives. Well, notice along the diagonal, it's just the second derivative with respect to x and respect to y. On the off-diagonal terms, we do one derivative with respect to x and one derivative with respect to y. This is just what follows from having the ij. If the two i's of the I and the j are the same, it's on diagonal. If they're different coordinates, it's off diagonal. But if we do all of those derivatives, we get this matrix here. And then to rewrite the Lagrangian, we have our kinetic energy term, which I've explicitly written in terms of vectors and matrices so you can see it, and then it might be easier to expand and just verify everything. And then we also take away our potential-like term. This, if you expand, would also look quadratic, but it may not be as obviously the same Lagrangian as what we started with. But if you expand everything, it will be a bit more clear that the Lagrangian hasn't really changed, it's just a coordinate change. And that's again because everything is quadratic. This final example, nothing's quadratic, or rather the potential terms are not quadratic, they're sine and cos functions. And so this one you really will have to do the Taylor expansion, and the final Lagrangian will be a bit different. So have a go on your own, and then come back to the video and I'll go through the solution. Okay, so the first thing we're going to do is expand around the critical point that's given by theta equals inverse cos minus g over omega squared L plus eta. And remember from the very first time we saw this Lagrangian, we had a condition on g over omega squared L that had to be between 1 and minus 1 for this to be well defined. So we're assuming that's true. And then we've also seen before that our kinetic matrix was just ml squared. Now the more difficult bit is going to be the potential-like term. So we take the second derivative with respect to theta. That gets us this really long expression. And now we want to evaluate it at the critical point. So the first thing we're going to do is rewrite sine theta in terms of cos theta. The reason I've done that is because the critical point is given by the equation cos theta equals something, and so it's just easier to rewrite cos theta than it is sine theta. So I've rewritten sine theta in terms of cos. And then we replace cos theta with g over L omega squared. And then we rewrite our Lagrangian, and this is quite complicated. You can simplify this. You don't have to at this stage. If you find it easier, you of course can simplify it. But notice that originally the Lagrangian wasn't quadratic, but now it is quadratic in eta dot and quadratic in eta. So what's nice is all of these Lagrangians were very different to begin with, but after you do some expanding, they're all kind of the same. The only difference is the sign of the potential and the constant in front of the eta squared, and whether or not it's a matrix, but either way the matrix would still just be constants. Now all the Lagrangians basically look the same. The equation of motion for all of them is basically the same. The proof for this is in your booklet, so read through the derivation and annotate it. For some of the steps, there might be maybe some subtle matrix manipulation. You will have to use the fact that all of these matrices are symmetric and constant. So how do we go about solving the equation of motion? Now, even though this looks complicated and it's a vector differential equation or a matrix differential equation, it's actually very similar to a second order differential equation like you might have seen in a normal differential equations course. And here it's just A equals 1 and C equals this K inverse V. And so just like for that differential equation, we try a general solution, and the general solution is the sum of exponentials. If it weren't for that eta, that vector eta sub A, everything here would be exactly the same as a scalar differential equation. But because it's a vector now, we have this vector eta sub A out the front. But the rest of the solution is something you'll have seen before. There's arbitrary constants in front of each term, and each solution is of form e to the lambda t or e to the minus lambda t. And then, because this differential equation is homogeneous, that is, it equals 0, if we find one solution and we find another solution, the general solution is the sum of those, which is why we have the sum over A. But really, the general solution is exactly the same idea as the scalar differential equation you would have seen before. The only difference is this eta A vector out the front. Okay, now we have our general solution. We want to find eta A and lambda. And to do that, we need to substitute this into our equation of motion. So let's substitute this in, and we'll do it term by term. So our first term comes from the double derivative and the e to the lambda t. Our second term comes from the k inverse and the e to the lambda t. Our third term is the double derivative with the e to the minus lambda t term in the solution. And our final term is the k inverse v, again with the e to the minus lambda t. Now we can factorize all of this together, and we have the sum over A, so we sum over all the possible solutions. Then we have this factor out this front, this lambda squared plus k inverse v. Then we have just the trial solution we started with. And so we want to set this equal to 0. And so in order to set this equal to 0, we can either just set our solution to 0, but then there's nothing going on. Alternatively, we set that bracket in the front to 0. And notice, because this is a vector equation, or a matrix equation, I am including the vector eta along with it. And we'll see why that's important in a minute. Now, you may have seen something like this before. In fact, you have seen something like this before. This is just an eigenvalue equation, where the eigenvalue is lambda squared, and the eigenvector is eta. So we are just finding the eigenvalues and eigenvectors of k inverse v. Now, normally, I know the eigenvalue is just given by lambda, but here it's lambda squared. And the reason for that is our solution has e to the lambda t and e to the minus lambda t. So each eigenvalue gives us a positive and a negative exponential. But lambda squared is still just the eigenvalue as you would normally find it from a linear algebra or vectors and matrices course. And that was all quite a lot of algebra, but to summarize, to solve the equation of motion, we find the eigenvalues and eigenvectors of k inverse v, where the eigenvalues are the lambda squareds and the eigenvectors are the eta. And then the general solution is given by the sum over all different eigenvectors. We have eta, and then the rest of the solution is e to the plus lambda t and e to the minus lambda t. So once we find the eigenvalues and eigenvectors, we just add them all together. And then A and B are going to be determined by the initial conditions of our system. So now we've seen how to find the solution. We find the eigenvalues and eigenvectors, and each eigenvalue corresponds to two solutions. Remember, it was lambda squared, so we have plus lambda and minus lambda in our solution. However, there are still three possibilities for lambda squared, and this might complicate things a bit. So lambda squared could be positive, it could be 0, or it could be negative. And we'll see if they make any changes or what these types of solutions mean. So firstly, we have lambda squared being positive. Now, this is what we call an unstable mode, and this is because it doesn't change the solution. So our solution is just the exponentials. So our system grows exponentially along an eigenvector. However, the solution is exactly the same as it was before. Secondly, we have lambda squared could be 0. And this is called a translational mode. The reason being, our solution doesn't grow or doesn't shrink or go back to equilibrium. Our entire system will just slide at a constant rate. And in this case, our solution does actually change. If we find our eigenvalues are 0, our solution will be something like this. So we still have our eigenvector, but it's going to be a constant times time plus a constant. This is what I mean by a translational mode. The whole thing just moves at a constant rate. And finally, we have lambda squared less than 0. And this is a stable mode, or an oscillatory mode, or a normal mode. And in this case, the solution doesn't really change. However, we can rewrite it. And we can rewrite it in terms of omega, which is equal to minus I lambda. And this turns our exponentials into complex exponentials. So we go from exponential growth and decay to oscillations. Okay, that was all quite abstract. So we'll go through our examples and see how we solve them. So we've already worked out our K matrix for this example, which is just M, our V matrix, which in this case is just K. And so we want to find the eigenvalues and eigenvectors of K inverse V. I mean, it's just a 1-by-1 matrix or just a scalar, so calling them eigenvalues and eigenvectors is just a bit of overkill really at this point. And we know that this is equal to K over M. So our eigenvalue equation is lambda squared plus K over M equals 0. And we can solve this to get lambda squared equals minus K over M. And because it's just a 1-by-1 matrix, there's no eigenvectors to really talk about. It doesn't make sense for a 1-by-1 matrix. So now we've got lambda squared is equal to minus K over M. This means it's a stable mode or a normal mode. And so it oscillates at angular frequency omega equals the square root of K over M. Remember, omega was equal to minus I lambda. And so this means our solution, in terms of complex exponentials, is the sum of the positive mode plus the sum of the negative complex exponential. And because this is complex exponentials, we could rewrite this in terms of sine and cos. It doesn't matter, it's just whether or not you prefer to work with complex numbers or you want to work with just real numbers. Okay, have a go at this example on your own and then come back to the video and I'll go through the solution. So you've already seen that the K matrix is M, that the V matrix is minus M omega squared, and therefore K inverse V is just minus omega squared. Again, it's a bit overkill to call these matrices. They're just 1-by-1 matrices or scalars. And so our eigenvalue equation is lambda squared minus omega squared equals 0, which means our solution is lambda squared equals omega squared. And that means our mode is an unstable mode. So we're going to have exponential growth as part of the solution. And our full final solution is a e to the omega t and e and plus b e to the minus omega t. So this is unstable because if we started off, as long as a is not 0, we're going to get our solution growing exponentially. Our second term will decay exponentially, but as long as a is not 0, that first term is going to dominate and we're going to have exponential growth. It's going to move away from the equilibrium point. Okay, for our final example, have a go on your own and then come back to the video when you've had a go. This one might be a bit harder than the previous one. So you've already seen in previous examples that the matrix K is just ml squared and the matrix V is given by this combination here. And that means K inverse V is given by this, which we can simplify to get this. And remember that when we found this critical point, we had to enforce that omega squared was greater than G over L. And so if omega squared is greater than G over L, then this combination is bigger than 0. And our eigenvalue equation, or our eigenvalue, becomes minus omega squared plus G squared over L squared omega squared. And this is less than 0. And because this is less than 0, our eigenvalue corresponds to a stable mode, a normal mode, an oscillatory mode, whatever you want to call it. And our final solution is quite complicated, or the coefficient of t in the exponential is quite complicated, but it's just the sum of a positive complex exponential and the negative complex exponential. So our system just oscillates around the angle defined by cos theta equals minus GL over omega squared. Okay, that lesson had quite a lot in it, but I'll summarize it all. So for any Lagrangian we can rewrite it in terms of a kinetic-like term minus a potential-like term. But what's important about the kinetic-like term is that it just includes the terms that are quadratic in the velocity. Then the location of a critical point, or the condition for equilibrium, is that the generalized forces are 0. We can then expand around the critical point, so we do a coordinate transformation. So Q goes to its QC, which is the value at the critical point, plus eta, which is the deviation from the critical point, or the equilibrium point. And we rewrite our Lagrangian in terms of these coordinates, and we Taylor expand. So eta is assumed to be small. So now our matrix K and this second derivative matrix are both evaluated at the critical point. So they're both just constant matrices. The equation of motion in this case simplifies to this for all Lagrangians. As soon as we write the Lagrangian in terms of the line above, all of the equations of motions are the same. And what differs is just the two matrices K and V. Then the general solution is given by the sum of e to the lambda t, e to the minus lambda t. And in order to find lambda and the vector eta, we need to find the eigenvalues and eigenvectors of K inverse V. And then depending what we get for the eigenvalues, if lambda squared is positive, then it's an unstable mode and the system exponentially grows away from equilibrium. If lambda squared is 0, then it's a translational mode and our solution will differ slightly. And if lambda squared is negative, then we can rewrite this, or lambda will be imaginary, so we can rewrite this solution in terms of complex exponentials. And the system just oscillates around the equilibrium point.